In 1915, a single man working in a quiet Berlin study wrote down an equation that unlocked the entire cosmos. Fact. But when his beautiful mathematics revealed a shocking truth about reality, he refused to believe it. And it became his greatest blunder. Theory. Welcome to the greatest plot twist in scientific history. Before we understand the mistake, we must understand the illusion he was trying to protect. Fact. For thousands of years, from Aristotle to the early 20th century, humanity held one unshakable belief: the universe was eternal, static, and unchanging. Fact. Then came general relativity. Albert Einstein proved that space isn't just an empty box. It is a flexible, invisible fabric called spacetime. Theory. Massive objects like stars and planets sit on this fabric, bending it like a heavy bowling ball on a trampoline. This curvature is what we feel as gravity. Theory. It was a masterpiece of physics. But there was a massive problem hidden in the math. A problem that threatened to destroy the eternal universe. Fact. Gravity is purely attractive. It only pulls. So, if the universe is filled with massive stars and galaxies, their collective gravity should be pulling everything together. Theory. According to Einstein's own pristine equations, a static universe was impossible. It should inevitably collapse in on itself under its own weight. Theory. Imagine realizing your math proves the sky should be falling, but you look outside and the stars are sitting perfectly still. Speculation. Einstein faced a choice: trust his revolutionary equations, which implied the universe must be in motion, or trust the millennia-old philosophical belief in an eternal cosmos. Fact. The prejudice of his era was simply too strong. He could not accept a dynamic, changing universe. So, he decided to fix his perfect math. Fact. In 1917, he introduced a mathematical Fudge factor into his equations. He called it the cosmological constant, represented by the Greek letter lambda. Fact. Lambda acted as an invisible, repulsive anti-gravity force built into the vacuum of space itself. It pushed outward just enough to perfectly balance gravity's inward pull. Theory. With this addition, his universe was safe. It was perfectly static. Beautiful, elegant, and completely wrong. Because deep in the cosmos, a rhythmic light was about to shatter his illusion. Fact. Einstein thought the universe was beautifully static. But to know for sure, humanity needed a way to accurately measure the unimaginable distances between stars. Fact. The key to unlocking cosmic distances wasn't found by a man with a giant telescope, but by a brilliant woman with a simple magnifying glass. Fact. Working as a human computer at Harvard in 1912, Henrietta Leavitt studied photographic plates of the small Magellanic Cloud, a neighboring dwarf galaxy. Fact. Her task was painstakingly tedious, cataloging thousands of individual stars by meticulously analyzing tiny, faint black dots captured on these delicate photographic plates. Fact. But amidst the monotonous data, she noticed something extraordinary about a specific class of stars known as Cepheid variables. These particular stars breathe. Fact. They actually pulsate, physically expanding and contracting, growing brighter and dimmer in a highly regular, rhythmic cycle. Exactly like a cosmic heartbeat. Fact. Leavitt made a profound connection. She discovered a direct relationship between how bright a Cepheid star actually is, and how slowly it pulses. Fact. She realized that the longer the star's pulse period, the greater its true intrinsic luminosity. This became known as the revolutionary period luminosity relation. Theory. Why is this revolutionary? Imagine seeing two identical streetlights. If one appears significantly dimmer to your eyes, you instantly know it must be further away. Comparison. By comparing a Cepheid's calculated true brightness to how dim it actually appears from Earth, astronomers could finally calculate its exact physical distance. Fact. Henrietta Leavitt had successfully discovered standard candles, immensely reliable cosmic yardsticks that allowed us to finally measure the true, staggering depth of our entire universe. Fact. Tragically, Leavitt received remarkably little recognition during her own lifetime, famously earning just 30 cents an hour for her paradigm-shifting astronomical calculations. History. She passed away before she could witness how her incredible discovery would directly shatter Einstein's beloved illusion of a perfectly static universe. History. Because armed with Leavitt's new cosmic yardsticks, another ambitious astronomer was about to point the biggest telescope on Earth at the dark night sky. Fact. And he was about to definitively realize that Albert Einstein's beautifully balanced, static universe was rapidly and completely falling apart. Fact. In the freezing dome of the Mount Wilson Observatory, Edwin Hubble pointed the massive 100-inch Hooker telescope at swirling clouds of gas called spiral nebulae. Fact. Most scientists at the time believed these nebulae were just small gas clouds inside our own Milky Way. But Hubble found one of Henrietta Leavitt's Cepheid stars inside one. Fact. Using her formula, he calculated its distance. The result was shattering. It was located an unimaginable 900,000 light-years away. Far beyond the edges of the Milky Way. Fact. In a single observation, Hubble proved that the Milky Way was not the entire universe. It was just one of billions of island universes drifting in the void. Fact. The universe had just grown millions of times larger overnight. But Hubble was about to find something even more disturbing than its size. History. Building on the work of astronomer Vesto Slipher, Hubble attached a spectroscope to his telescope. This device acts like a prism, splitting a galaxy's starlight into a rainbow. Fact. Chemical elements in the stars absorb specific colors, leaving dark vertical barcodes across the spectrum. These lines are the unique fingerprint of the galaxy. Theory. But Hubble noticed a bizarre pattern. The black barcodes for almost every galaxy he observed were shifted out of place, moved towards the red end of the spectrum. Fact. This phenomenon is called redshift. And to understand why it was the final nail in the coffin for Einstein's static universe, think about an ambulance. Theory. When an ambulance drives toward you, its sound waves are squashed together, making a higher pitch. As it drives away, the waves stretch out, lowering the pitch. This is the Doppler effect. Comparison. Light works exactly the same way. If a galaxy is moving away from us, the light waves it emits are literally stretched out as they travel across space. Theory. Longer light waves appear red to human eyes. Therefore, if a galaxy's spectrum is redshifted, it means the galaxy is physically moving away from Earth. Theory. And Hubble's data was staggering. Almost every single galaxy he looked at was redshifted. The entire cosmos was rushing away from us in every direction. Fact. Even crazier, the further away a galaxy was, the faster it was retreating. The galaxies weren't just flying through space. Space itself was expanding, carrying them along. Fact. In 1929, Edwin Hubble published this monumental discovery. The static, eternal universe was dead. The universe was growing. Fact. Hubble's undeniable observation of receding galaxies presented a terrifying logical question for the scientific community. If the universe is growing larger today. Fact. What happens if we run the cosmic clock backward? The galaxies must have been closer together yesterday, and even closer a million years ago. Theory. Keep rewinding, and eventually, all the matter and energy in the entire cosmos must crush together into a single, unimaginably dense and hot point. Theory. 2 years before Hubble's telescope proved it, a brilliant Belgian physicist and Catholic priest named Georges Lemaître had already predicted it using pure mathematics. History. Lemaître looked at Einstein's original equations, without the fake cosmological constant, and realized the math naturally described a universe that was actively expanding. Fact. He proposed what he called the hypothesis of the primeval atom. The radical idea that the entire universe was born from a single, superdense quantum seed. Theory. Today, we know this concept by a much more famous, and originally mocking, name given by its critics, the Big Bang. Fact. It wasn't a destructive explosion in space, but a majestic unfolding of space itself, creating time, matter, and the very fabric of reality from nothingness. Theory. For a Catholic priest to suggest the universe had a definitive genesis moment was considered scientifically scandalous and deeply suspicious at the time. History. When Lemaître first presented this brilliant idea to Albert Einstein in 1927 at the prestigious Solvay conference, Einstein's reaction was famously brutal. History. Einstein, unable to let go of his beliefs, notoriously told the young priest, "Your calculations are correct, but your grasp of physics is abominable." Fact. Einstein was still desperately clinging to his cosmological constant, his mathematical shield protecting the eternal, unchanging cosmos he philosophically preferred. Fact. But Lemaître didn't back down. Because unlike Einstein's purely philosophical preference, Lemaître had the pristine, undeniable equations of general relativity on his side. History. And soon, Hubble's undeniable telescope data from Mount Wilson would arrive in Europe, forcing the greatest mind of the 20th century into a corner. Fact. The universe was changing, evolving, and growing. Einstein's beautiful illusion was finally shattered, and he traveled to California to see the proof with his own eyes. Fact. In 1931, Einstein completely abandoned his static universe model. He scrubbed the cosmological constant, his beloved lambda, from his equations. Fact. According to his colleague George Gamow, Einstein later referred to the introduction of the cosmological constant as the biggest blunder of his entire life. History. The case seemed closed. The universe started with a big bang and has been expanding ever since. But a massive question remained. Fact. Since gravity is an attractive force, the collective mass of all the galaxies should be pulling against the expansion, like a stretched rubber band trying to snap back. Theory. For decades, astronomers safely assumed the universe's expansion was slowing down over time. The only debate was whether it would eventually stop, or completely collapse back in on itself. Theory. Fast forward to 1998. Two independent teams of modern astronomers set out to measure exactly how fast this deceleration was happening. History. To look deep into the past, they needed something much brighter than Leavitt's Cepheid stars. They needed cosmic fireworks, type Ia supernovae. Fact. These are catastrophic events where a dead white dwarf star steals too much matter from a companion, reaches a critical mass, and undergoes a massive stellar burst. Theory. Because they all burst at the exact same mass limit, they all shine with the exact same peak brightness. They are the ultimate, perfect standard candles for measuring the deepest cosmos. Fact. But when the data from these extremely distant supernovae came back, something was terribly wrong. They were 25% dimmer than anyone expected. Fact. If they were dimmer, it meant they were further away. And if they were further away than the deceleration models predicted, it meant only one impossible thing. Theory. The universe's expansion was not slowing down. It was speeding up. The galaxies were being pushed apart faster and faster every single second. Fact. To accelerate against the immense crushing gravity of billions of galaxies, there must be a repulsive force. An invisible pressure built into the vacuum of space itself. Hypothesis. We have no idea what this phantom force is. But it is stronger than gravity. We gave it a mysterious name, dark energy. Hypothesis. And the most terrifying part? Dark energy isn't just a tiny anomaly. It makes up approximately 68% of the entire universe. Fact. This mysterious dark energy is pushing the cosmos apart. And the most ironic part of this modern discovery? The math perfectly matches an old, discarded idea. Fact. To understand it, we have to go back to that dusty chalkboard in 1917, and the mathematical symbol one man desperately wanted to forget. History. Remember the cosmological constant? The mathematical Fudge factor, represented by the Greek letter lambda, which Einstein used to artificially keep his universe static. Theory. He called it his biggest blunder because he used it for the wrong reason. But mathematically, lambda is the absolute exact description of modern dark energy. Fact. Lambda represents a constant energy density inherent to the vacuum of space itself. As space expands, more space is created, meaning more dark energy pushes back. Theory. Einstein's discarded mistake has been resurrected. Today, it forms the crucial foundation of our standard model of cosmology, known as the Lambda CDM model. Fact. But why does empty space have energy at all? To answer that, we must zoom past the galaxies, past atoms, down to the deepest quantum realm. Theory. Quantum mechanics tells us that a vacuum is never truly empty. It is a boiling sea of virtual particles constantly popping in and out of existence. Hypothesis. This quantum foam generates a baseline vacuum energy. But there is a massive, embarrassing problem when we try to calculate how strong it should be. Fact. Quantum equations predict that dark energy should be a 1 followed by 120 zeros times stronger than what we actually observe in telescopes. Fact. Physicists call this the vacuum catastrophe. It is widely considered the single worst theoretical prediction in the entire history of physics. History. Despite not understanding its quantum origin, we know its cosmic power. Today, we realize that everything we can see, stars, planets, and ourselves, makes up just 5% of reality. Fact. Another 27% is invisible dark matter holding galaxies together. And the dominating 68% is the phantom force of dark energy, dictated by Einstein's lambda. Fact. So, was it really a blunder? His equations were so profoundly perfect that even his forced, artificial, mistake ended up describing the ultimate fate of reality. Theory. He was wrong about a static universe, but absolutely right that the vacuum of space possesses an invisible, governing energy. A genius even in his errors. History. Because dark energy is constantly accelerating the expansion of space, it forces us to confront a chilling, yet awe-inspiring vision of our ultimate future. Theory. If this phantom force continues to dominate, the universe will not collapse back on itself. Instead, it will face a fate known as the Big Freeze. Theory. Also known as the heat death, this isn't a fiery ending, but a slow, graceful fading into absolute stillness and unimaginable cold. Speculation. Let's run the cosmic clock forward. In about 100 billion years, the expansion will be so rapid that light from distant galaxies will no longer be able to reach us. Speculation. They will simply fade past the cosmic event horizon, disappearing from our night sky forever. Future civilizations will look up and see nothing but an endless, empty black void. Speculation. Any astronomers living in that distant era will have absolutely no evidence that other galaxies ever existed. They will logically conclude their isolated island of stars is the entire universe. Theory. The beautiful cosmic web that Edwin Hubble discovered, and that Albert Einstein's math unknowingly predicted, will be completely hidden from the visible record. History. Fast forward to 100 trillion years from now. The last clouds of star-forming gas will be completely exhausted. The final, faint red dwarf stars will slowly cool down and go dark. Speculation. The universe will go pitch black. The only remaining objects will be silent, cold remnants, dark white dwarfs, neutron stars, and supermassive black holes. Speculation. It will be a universe of ghosts, wandering blindly through an unimaginably vast, freezing, and ever-expanding vacuum. Speculation. But even these dark cosmic titans won't last forever. According to physicist Stephen Hawking, over unimaginable timescales, black holes slowly leak radiation and evaporate. Theory. It will take approximately 1 Google years, a 1 followed by 100 zeros, for the last supermassive black hole to gracefully dissolve into a faint mist of pure energy. Fact. At this point, the universe reaches maximum entropy. A state of perfect, unchanging equilibrium just a fraction above absolute zero. Time itself practically loses all meaning. Theory. It sounds melancholic, perhaps even terrifying. But there is a profoundly beautiful realization hidden in this timeline of the cosmos. Philosophy. We happen to exist in the exact golden era of the universe. A brief, vibrant window where the cosmos is glowing with stars, and the history of creation is still visible in our sky. Philosophy. Albert Einstein famously called the cosmological constant his biggest blunder. He spent his later years regretting that he didn't trust his own beautiful equations. History. But the story of Lambda teaches us the ultimate lesson about science itself. It is never a straight, perfect line to the truth. Philosophy. Science is a messy, beautiful, collaborative process of trial, error, and paradigm shifts. It requires us to abandon our deepest prejudices when reality proves us wrong. Philosophy. It took Henrietta Leavitt's meticulous, underappreciated measurements of pulsing stars to build the very first cosmic yardsticks. History. Edwin Hubble's freezing nights at the massive Hooker telescope observing the redshift of fleeing galaxies. History. And Georges Lemaître's absolute courage to follow the math backward, daring to propose a singular genesis point for the entire universe. History. All leading to modern astronomers mapping distant supernovae, finally shattering the illusion of a static universe and uncovering the phantom grip of dark energy. Fact. We are standing on the shores of an expanding cosmic ocean. A universe that is larger, stranger, and more dynamic than our ancestors could ever have dreamed. Philosophy. We are just a tiny, momentary species living on a pale blue dot, drifting through a seemingly infinite, accelerating vacuum. Philosophy. But we possess something truly extraordinary. The ability to look up, to build lenses of glass and mirrors of gold, and to decode the ancient light of the stars. Philosophy. As Carl Sagan once profoundly said, we are a way for the cosmos to know itself. Philosophy. So the next time you make a huge mistake, don't be too hard on yourself. Just remember Einstein. Because sometimes, your biggest blunder might just be the key to the universe. Conclusion. If you enjoyed this journey through space and time, make sure to hit that subscribe button to join our cosmic crew. Outro. Keep looking up, keep questioning the universe, and I'll see you in the next exploration. Farewell, fellow travelers. Outro. Thanks for watching. Outro.